Good morning, all of you. So, some note points about modulus of elasticity. See, generally, what we will think that if any material is elongating more, yes, or the material which stretches more, it is more elastic. But actually, it is not. Understand? So, what is that? The material which stretches least, okay, is considered to be more elastic. So, see here, what I am writing. A material which stretches more is not more elastic. Keep it in mind, right? Material which stretches more is not more elastic. Keep it in mind. Whereas, whereas material material which stretches to which stretches to a lesser extent for a given load is considered as more elastic. For example, see, if suppose I am having steel and rubber applied to, or I will write like this, you will understand easily. If I have taken rubber and steel, which will and applied some load to that too, which will elongate more rubber, which will elongate less steel. So therefore, can I write here steel is more elastic. Steel is more elastic than rubber. Understand? You see a steel, you take a steel rod and take rubber, applied some load, rubber will extend more, steel will extend less. Then also, which one is more elastic? Steel. Steel is more elastic than rubber. Understand? Right? Next one, for perfectly rigid body, see next note point, for perfectly rigid body, delta L 0, yes. Next delta V 0. Next phi also 0. So what will be there? All will be 0, hai na? Yes, or infinity. Yes, all will be infinity. That's why y, eta and k will be infinite will be infinite. Yes, and therefore elasticity of rigid body is infinite. Okay, right? Next one. Now suspension bridge in this, there is a stretch in the ropes. है ना? Have you seen? I think some Wild versus Man one serial is there, adventure serial. One episode is there, I think so. So in that, he will climb, or there will be one suspension bridge above the water. Yes. So when someone will walk or use that bridge, there is stretch in the rope. Yes. And then the elasticity involved is what? Linear or tensile. Suspension bridge, elasticity involved. This is just take it as a note point so that you will understand elasticity involved is which one? Linear or tensile? Linear or tensile. Okay. Next one, automobile tire. Next one is what? Automobile tire. Automobile tire. Tell me which one? Now here air is getting compressed. So change in volume, and therefore which type? That is bulk. Yes. Next one, coiled spring. Coiled spring. Here which one? Shear. Why? Because it will get twisted. है ना? This is shear. Yes. And water lift pump. Next one, water lift pump. Water lift pump. So again here also water is getting compressed, and that's why here also which is bulk modulus of elasticity. Next, rubber heels. Rubber heels, we know we are wearing some chappals. You know? So when we are applying pressure or there is a weight on it, you know, so that weight, because of that weight, that heel shape is going to change, and therefore this is again what? Shear, because here shape is going to change. Yes, shear, right? And here modulus of elasticity decreases with temperature. Decreases with temperature. Understand? Note down. Finished? Next one. Now, electric or telephone poles are there. Have you seen? Electric or telephone poles. Electric and telephone poles given hollow shape, given hollow structure. Why? Because they will have greater moment of inertia, and hence because of this greater moment of inertia, so what will happen? Less deformation. Less deformation. Understand how we are using this in our general life. Next point, next note point. So a shear is there, na? Shear means change in shape, where you will get particularly cutting. Next, hammering. Yes, cutting, hammering, and twisting. Cutting, hammering, and twisting. Right? And one more point you can note down. Elasticity of material. Elasticity of material. Elasticity of material get affected by following. Number one, hammering and rolling. What will happen? Hammering and rolling, because of this elasticity increases. Second one, annealing. Annealing means formation of larger crystal. Formation of larger crystal. Then in this case, it decreases. Next point, if we will add now impurities, means some other mixture we have added, so presence of impurities, presence of impurities, so may increase or decrease. Okay, may increase or decrease, that is depending on what you are adding, how much you are adding. Next one is increase in temperature. Already I told, temperature increases, elasticity decreases. Elasticity decreases. This is what the note points, right, about this moduli. You can just note down, and how we are using in general life, or some examples which I have told. If you will read that, you will get clear cut idea, right? So let's move ahead now. Next, Poisson's ratio. What is next topic? Poisson's ratio. This is not any Poisson ratio, okay? This is not any poison. This is name of a scientist, of course. Poisson's ratio. Okay. So first, before going forward, this side I will give you two definitions which are important for understanding this Poisson's ratio. So that is lateral strain and longitudinal strain. Okay. What are the two definitions? I am writing here in this corner so that you will understand what is this Poisson's ratio. So I am using this corner for that. Lateral strain. Lateral strain means the ratio of change in radius, ratio of change in radius or change in diameter to the original radius, to the original radius or diameter is called lateral strain. Got it? So how I can define this lateral strain, or how I can write formula? See here, lateral strain is equal to delta D by D. So delta D by D, or you can write delta R by R, and this is minus. Okay. Next one is longitudinal strain. What is next one? Longitudinal strain. Longitudinal strain is what? You know this. Elongation by original length, है ना? Already we have learned this. So longitudinal strain is nothing but change in length to the original length, है ना? Change in length to और by original length, है ना? by लगाएंगे इसको. Change in length by original length. Change in length by original length. Change in length by original length is what? Longitudinal strain. And therefore longitudinal strain formula, if I want to write longitudinal strain is equal to delta L by L. Now Poisson's ratio is what? See here, Poisson's ratio. In one line I am writing, that is what? Ratio of lateral strain to the longitudinal strain. Ratio of lateral strain to the longitudinal strain. The ratio of lateral strain to the longitudinal strain. And it is denoted by sigma. Sigma is equal to what? Minus delta D by D total divided by delta L by L. Clear? Understood this Poisson's ratio? Yes. Why we are using this negative sign, sir? Here also negative sign. They are in what you can say bulk modulus. Also we have used negative sign. They are in bulk modulus negative sign for compression. But what is use of here minus, or what it indicates minus sign? Shall I write here? Wait, I will write. Minus sign indicates minus sign indicates as length increases, as length increases, as length increases, diameter decreases, है ना? Diameter decreases. That's why we are getting this minus sign. Keep it in mind. Okay. So usually जो theoretical limits है, theoretical limits of this sigma, theoretical limits of this sigma is from -1 to plus 0.5, -1 to 0.5 plus 0.5. Okay, how much it is? -1 to -1 to plus 0.5. Now, what is the ratio? What you can say unit of this Poisson's ratio? What will be the unit? No unit. Why? Because here also no unit, here also no unit. So I am writing here no unit. Keep it in mind. No unit. There is no unit for this Poisson's ratio. And practical limits for this Poisson's ratio is from 0.2 and 0.4. 0.2 and 0.4. Right? Understood? Okay, note down. Finished? Okay. Next. Now relation between relation between volume strain, lateral strain, and Poisson's ratio. Relation between volume strain, lateral strain, and Poisson's ratio. And Poisson's ratio. Volume strain, lateral strain, and Poisson's ratio. Okay. So see, consider a wire of length L and radius R. Then its volume V is equal to pi R square L. So now here pi is constant. Yes. Shall I draw one diagram? Wait. This is wire. Okay. I'm just writing or drawing little bit big wire, so that means magnified view we can say, so that we can indicate even radius of cross section and length also. Yes. Can you see? This is a wire whose length is how much? L, and this is what radius is R. Okay, this is what radius R for this. And then volume is equal to what? V is equal to pi R square L. V is equal to pi R square L means here pi is constant. So if I want delta V by V, then how I can write 2 into delta R by R plus delta L by L. Okay, right? So now this is what delta V by V, but we know sigma is equal to, just now only we have seen one relation, that is minus delta D by D or delta R by R. I can write anything. Minus delta R by R by delta L by L. So therefore, can I write like this, that minus delta R by R is equal to this, I am transferring here, so sigma into delta L by L. Okay, sigma into delta L by L. Now this part is there, I will substitute here. So this is my equation number 1 and this is my equation number 2. So therefore delta V by V is equal to 2 into, this is minus delta R by R, so I am writing minus sigma into delta L by L plus delta L by L. Okay, now see what I am getting, delta V by V is equal to minus 2 sigma delta L by L plus delta L by L, and I'm taking common delta L. So here delta V by V is equal to delta L by L into 1 minus 2 sigma, 1 minus 2 sigma. Understand? So this is what the relation between volume strain, this is lateral strain, and this is Poisson's ratio. Clear? Understood? Okay. So note down. Okay. So let's stop here for today. Bye.